1, 2, 3, 4, 5. Hello dear viewers, finally we are starting our second part. I think that's the second out of 3. I hope that's the second out of 3 because article is big and that's the biggest article that we have ever discussed during this whole history of streams. And I also hope that my app will work fine. That's what I should just hope. And also there is 34 degrees right now. That's the first day of August. Still summer, it's very hot. Usually I do streams in the evening, but right now I need to do it now because otherwise I will not have time to finish this very big article. Okay, so let's now jump to the article itself, and that's the continuation of the previous discussion. So that's the top of the canvas. I was wondering why I can't scroll up, but that's the highest part of the canvas. So a very, very quick reminder what happened during the previous stream. So we went through the abstract, summary, and introduction to the paper on the origin of charge density wave in select layered transitional metal Dichalcogenides. Let's check the title because I'm confused a little bit. Yeah, that's the first time I think about this word select, but it's meant about these 3 selected 2 materials of one family of materials, and they have special properties, a lot of special properties actually, but the main property and all the talk is about this main property, and that's the property of charge density wave. So the charge density wave is the modulation of both periodic atomic lattice and electrons on top of this atomic lattice. And in summary, Rossnagel told us that a lot of research should be done should be still done. And right now I don't remember on top of my head what is the real value of the summary and conclusion, but the value of the article is that it summarizes a lot of experimental results and a lot of theoretical approaches and gives a lot of useful statements. So that's the review paper, which gives us a lot of useful references, but not so much explanation is present in the article. So a lot of things are still unexplained. And the introduction was basically that there is this charge density wave, and people study it, and there are some experiments. That was basically the introduction. So let's now continue from the second part out of 5, and today the plan is to do third and second part out of 5 parts. And currently I have read okay, let's check just a preview until which part I have read. I have read until the 1/3 of the 4th part. So I will need to finish the 4th part, but also I have read a little bit on the middle of the 4th part and also end of the 4th part, and yeah, and also some parts of the 5th part, so it shouldn't be a big problem. And tomorrow I hope to finish this article. And let's just jump like this to the second part. So here in the second part, the charge density wave formalism will be introduced. And that's the typical formalism. Okay, that's the Rossnagel's version of the typical formalism. There are other books which are about purely charge density wave, and I wasn't reading them for half a year or even more. I think it was November the last time when I was reading papers about charge density, I mean books about charge density waves. But right now I have this wonderful app and a lot of motivation to finally understand the charge density wave. So maybe some of the near future streams will be about purely charge density wave theory. But here, that's Rossnagel's version of typical list theory. And let's go, as we always do in the streams, through all the statements. So one of the things that I want to point out initially after reading what is further is that you need to pay attention about dimensionality of the materials, because later he will say that, so as I was speaking in the last stream, there are these three materials, and both of them have charge density wave, and the big part of the big value and big part of the article is the discussion of which models are applicable for all of these materials. And this discussion boils down to analysis of dimensionality, or more precisely effective dimensionality, since all of them are three-dimensional, of course, but physics in some of them can be lower dimensional. So for example, I'm just jumping far ahead on the third section that will be in the end of the stream. He will say that this material is approximately, well, it's two-dimensional. That's somewhere in between of two and three-dimensional material, and that's one is less than three-dimensional material. So in scope of all of these plots and in scope of all the formulas that we have in theory, it's important to track from the beginning the dimensionality. And right now he starts discussing one-dimensional model. However, later he will be discussing for a long time that one-dimensional model is actually not applicable model, or maybe there are a lot of, I mean, to tell you more precise, there are a lot of complicated features appear when we try to use this theory for three-dimensional, two-dimensional materials. So right now I even don't understand why do we need to start from this theory at all. Maybe we should just start from tight binding models, and that's what I also noticed during the previous stream. Yeah, maybe it's written in my list of questions which I will fill after all this series of streams. That, like he will say later that, hey, we have a tight binding model that gives us good results, so why do we need at all this very peculiar theory that doesn't fit to the typical formalism by default, and you need to have some extra derivations. But these extra derivations can be a part of my future streams. So if you want to have streams about them, just write in comments and maybe I will arrange it. If you really want, then I will definitely arrange it. But okay, let's just put aside these comments about future implementation and focus on the theory here. So we are proposed to see to work with the modulation of electron density, and here rho zero, it's a little bit a problem because it's unperturbed electron density. So by default, okay, by default I guess it's also periodic, but usually we just assume it as a constant, which is very unphysical, because it should be like periodic if we have ideal crystal, and if the crystal is not ideal, then some defects can influence this periodicity. I was just thinking about it because one can think that it's obvious what happens here, just modulation, and rho1 is a bad notation because it should be dimensionless, but from this notation, one can think that rho 1 is the same dimension as rho 0. But these are rather details of notation, not the best notation, but okay, it's not a real problem. But the thing that we don't know anything about rho 0, it's a, strange thing, because I was always thinking that it's a constant, but later, while I was reading, I found a place where, yeah, where it's not really obvious that it should be a constant. And that's not, because like I would spend way more time, would not do this presentation because it would be way more uncomfortable. So this is an image that should be kept in mind during all this discussion of typical chart-density wave theory. Here, okay, so let me click like this and then check the screen. So that's the feature of Slovenia, that the internet is a little bit broken here. Don't know much about the signal, so I hope that it will work, but I don't know. The big problem appears with this internet. And okay, let's try to reconnect to the Wi-Fi. Okay, so seems that it works, and I have a little delay from my phone where I see what happens on my screen, because there is no way to do it other way, but seems that it works. Okay, so and let's just continue and hope that internet will not fail again. So here we need to just think about it as a simple model, which should have all the physics that we want. And later we will have some citations which, and Rossnagel claims that these citations confirm that that's the modulation of, this theory is indeed applicable for that materials. But here in this paper, there is a big discussion about if this model is applicable or not, and what should we do with this model to make it applicable. But only what we see in this article are the references and the statements. Okay, that's the chart density wave, the modulation of the electronic charge. Why is it wave? Because maybe, definitely there are some studies about transport of such waves, so maybe it's like a wave, but currently it's a standing wave. Well, like cosine is the harmonic, so you can call cosine a wave also. And here the Q0, I think, is a fixed thing in notation, and also lambda 0. Sorry for a second. So lambda 0 is also a fixed notation for the wavelength. So that's the typical optical notations like wave vector and wavelength. So the same thing is here. Yeah. So I'm just trying to think a little bit deeper that, okay. Vector. Okay. Okay, so that's just a typical optical notation. Now there is the second formula, which is the one that I don't understand fully, because there is a deformation of the lattice, and the deformation corresponds to the modulation of the electronic density, but it looks very different. Here we have sine, here we have cosine, and we have some integer which defines position of ions. So right now I can't comment this formula at all. Looks very different, and nothing is explained about it, so I will not also explain anything. Anyway, the main message is that there is a modulation of atomic displacements, and we should keep in mind this image which I selected as the most important image. So if we had one-dimensional solid, then we would have such little displacements just along one line. But okay, that refers us to the typical theory of chronicity wave, which is not in this article and not also in my head, so I can't comment more than what's written here. Here it's written that if we have such a modulation, then we can use screening theory of electron, like from solid state physics, and we can derive this formula. Of course, I haven't tried it, and I need to search for this screening theory, which is really meant here, and I haven't done it. So what we are told is that this directly somehow implies this. Maybe we don't need some advanced theoretical formalism from it, and we need just this typical Maxwell's laws. But okay, I wasn't going to this direction, so I just understand that's written here that this from this formula you can obtain this formula, and from this effect, which is intuitive. Okay, I mean the intuition is maybe if we have like periodicity, then in one parts of the lattice there are higher potential, there is a higher potential, another part of the lattice there is lower potential, so electrons will sit in lower potential more, so that's intuitive thing. And here they say that PLD, periodic lattice distortion, and chronicity wave always come together. I don't know what is in the cited papers, but that's very intuitive, that there is modulation of both of them. So yeah. And here there are 4 questions that arise. Okay, the first question, what is the driving force? I consider is a useless question because I think that it should be possible to derive first from second or second from first. And nothing is driven here, so we don't know how to do any of the both derivations of both directions, and that's like really a useless question, but still that's what Rossnagel writes as the first question. The second one, let me check what's written here. Okay, there are 2 questions in scope of his second question. The first question is about stabilization, and later he will tell us that there is some criterion which is just cited from the paper, so I don't know any, I mean, I don't understand much on intuitive level of this stabilization. And also it's not clear what are the perturbations like based on which we claim that like for which we claim that it's stable. It's not written also why do we really need to think about stabilization. Yeah, like there are some fluctuations, but they're always there. But anyway, okay, there is this part of theoretical analysis about stabilization of this new state. Second thing is the microscopic origin, and that's a deep question which will be mentioned throughout this article. And the conclusion is that we don't know any microscopic origin. However, it's really a good question that like okay, so I wrote myself a question that microscopic origin, one can say, hey, that's like typical electron-phonon interactions, like a Fröhlich model. Maybe they say that actually Fröhlich model is for little coupling, we need a big coupling, but still, like as far as I understand, the most general model is the Fröhlich model. So I don't know what do they mean by microscopic origin. Maybe if you know that some properties are not derived from the Fröhlich model, then you can pose this question about another microscopic origin. But for now, I don't understand really why this question is still here. But okay, that's his second collection of questions. The third question is the one that I haven't seen throughout this article yet. Maybe it will be in the fourth or and fifth part. But it's about the influence of the charge density wave and lattice distortion to electron-phonon spectra. And actually, okay, yeah, no, maybe I was confused. Maybe it's actually written here, even shown here. So that's the inference. So maybe if you are asked this question, then you can just show this plot. Look, a lot of things happen. Like there is a big degeneration of the band in the non-distorted case, and the like a lot of bands appear, spectral weight becomes different, and that will be the end of today's stream to discuss what happens. So it's not like a signature in the spectrum, it's purely a change of a spectrum. But that's about electronic spectra, and we'll just check what is about C here. No, that's also, I guess, electronic spectra. So I don't know anything about impact to phonon spectra. It's actually a good question. Okay. And I noticed that I didn't plug my phone to a charger. I have done it. Okay. So one question will be answered in detail, another question will be not touched, definitely during this stream. And the last question, yes, and the last question is the question about typical theory, that in typical theory we have a weak coupling, and so it's not clear here what do they mean by this formula U0 divided by A, because it relates us to this formula, but they don't explain what is UN at all. So maybe we should understand U0 as this term in the electronic lattice distortion, but again, everything here just, I mean, it should be taken just from some book, so it's better to read the original book than to read this paraphrased version. But I think that's what happens here, that if this amplitude of displacement is little compared to the lattice constant, then we call it a weak coupling, because all the properties are not changed much comparing to the distorted case, when there is no electron-phonon coupling at all. And just wanted to remind that everything here is about electron-phonon interactions. So that's the special approach for electron-phonon coupling. So if there is no coupling at all, then nothing will be here, none of these pictures. I mean, the right part of the picture will be not like this. It's actually really a good question. Like, if there is no electron-phonon interaction, how would the Fermi-surface look like? But I guess the same. Let's write it. Okay, I will try to understand this question later, but I assume that still there will be a particular form of Fermi surface, and on top of it we have the electron-phonon interaction. That just links us to the typical theory of condensed matter Fermi surfaces, where we were introduced to different shapes of Fermi surfaces, but right now I don't remember why the shape of Fermi surface changes such in a such way, like it's done here. And it's also like, I mean, that brings us to the question if this picture is for if this picture is for charge density wave, and as first remember that's for charge density wave state. Oh no. First remember that's for normal state where there is no modulation. That's just the Fermi surface, and then these vectors, red vectors, will be telling us something about the modulation that possibly can occur. And okay, we'll go to it later. What's written here? Here it's written that we will study one-dimensional theory and then struggle a lot and cite a lot of papers about generalization of this theory for higher dimensions. However, it's like quasi two-dimensional material, so it's not clear what do they mean by dimension at all. It's definitely not purely two-dimensional materials. And later, as I was announcing, it will be stated that the third material is nearly three-dimensional material with three-dimensional charge density wave. But okay, if we have easy one-dimensional, I mean relatively easy one-dimensional theory, then we can pose this question about generalizations of this theory, and it requires a good education, a good deep understanding of this one-dimensional theory to do these generalizations. Yeah, and I didn't summarize these answers. I will do summary a little bit later. So, okay, let's just look at our plan, and our plan is written here, and I can do even the magic detachment, and that's our plan with some little bugs in displaying, but it doesn't matter. So we will go to the parallel instability, and then discussion of all these two effects which I just have announced. Then there will be electronic insulator instability, which is a special effect, and some discussion of applications of this theory. So let's just go to the first part, and we will need this picture to be opened near us. Okay. Okay, right now I'm confused that it's written as the consequences of strong electron-phonon interactions, because I was telling you before that as far as I understand, here we start with weak electron-phonon interactions and then we generalize this theory. But here a strange statement is written that it's a consequence of strong electron-phonon interactions. So let's just read what's written next. Yes, so there are typical words that are pronounced when people discuss parallelist model, is that both these modulations result in that there is a gap in the electronic spectrum near Fermi-surface, and that's why it's more favorable for the state to occur, because total energy of this state will be lower. And currently already have answer to this question, which was written like 5 maybe days ago. So gain and loss, I mean, it will be also commented further, but gain and loss argument is that if we have less energy, then it's energy gain. If we have more energy, then energy loss. And we need to find the state which will have lower energy. That will be the state in reality. And if we want to go to the state from another state, then there will be some excitations or some radiation or something else, which will take out the rest energy, which will not be there at the final state. Okay. And what is the self-sustaining? It's not clear here, but the idea is that that's just a good theory that has no contradictions. That's what I assume by self-sustaining. Okay, here nothing is really important. There are synonyms. So if you want to write complicated theory, then you can use the synonyms and call parallel instability, which is called structural phase transition, because structure changes. And again, we have emphasis that it's only when we have a strong electron-phonon coupling. Okay, here they cite one paper with which they don't agree, but for now it's not really important. And we also don't see any explanation what do they mean by accidental byproduct, but maybe the main idea of this question is that one can use different synonyms to the, I mean, different adjectives to this phenomena, and or different approaches, but we don't know anything about theoretical approaches, and this paper tells us nothing except citations. But okay, in some other works there are other views on, I mean, at least in this work there is another view on this effect, and they consider some periodic lattice as a byproduct, but it's not clear what do they mean by this consideration as a byproduct, so let's just keep it. The conclusion is that some people can describe it in a slightly different way, which always happens. And right now we see the plot that's already for a long time near us. That's a schematic well-known plot. Let's just describe shortly what happens here. So that's the distortion of the electrons in the one-dimensional solid. Here we have a distortion of lattice, so some atoms are shifted to some positions, like they are shifted to one position, they're both shifted also to the same center, and so on, so on. So that's how both distortion occur. Then this plot tells us that there is a energy gap in electronic spectrum. So in this model we assume typical energy band of this type, and maybe if we have holes, if we have a semiconductor, then we'll have this type. but I wasn't thinking much about this like turned upside down dispersion. That's just my intuition of how it can occur. And if we have a coupling of electrons and lattice, then there is the gap. So by default, that tells us that all one-dimensional solids are gapped, because right now we don't see any reasons why this theory shouldn't be applicable for a typical solid. But that's not the truth. And actually it's hard to find. I mean, I don't know about these nanowires. Can they be considered really one-dimensional, or we need to have a special material which is a quasi one-dimensional material? But that's the typical picture. And also we have a density of states, so how many states are at the special values of wave vector. And I don't know about this gray area, unfortunately. What does this gray area mean? But the red area means the density of states. So density of states is higher way below and at the maximum level, at allowed level near Fermi-surface above and below. So maybe we'll return to this discussion of density of states later. But right now, that's the final statement about this effect, that such modulation is there. And right now we need to wait a little bit. And okay, so the third picture is about already phonons. So for some reason, we also consider the Debye model, but by the way, it's actually a really good question. So here we have a Debye model. Debye model assumes that there are only phonons of this type of dispersion, and we don't have real phonons actually, because that's just approximation. Real phonons will have much much more different dispersion. It will be non-homogeneous. It will have some jumps, but here there is just this linear, not linear, but here linear, then not linear, but smooth dispersion. And the prediction is that because of this coupling of electrons and phonons, will fall in the frequency of the phonons. How this frequency is used in theory, I guess, I don't know, but maybe. Okay, actually, it's a good question about the theory. Okay, so that's the theoretical question which I should approach one day. Here in this more review article, nothing is written about it. It's just the question that like here the frequency of phonons is changed. So how we taken into account frequency, this change of frequency when we were spoken about electronic spectra? And I don't remember that we have to have taken this into account. However, we should have taken it. So I need to double check that that happens there. So someday, maybe in a week, we will have, maybe in several weeks, we will have a theoretical stream about effects in electrons and phonons, because understanding of this requires definitely a good preparation of electrons and phonons. But let's look the caption to this figure. Yeah, so everything is here what I told you, except that there is the comment about this boldness of the line, and boldness corresponds to spectral weight, and that's not the thing I can comment right now. I don't remember also discussion of it, but because of some reason it's stated here that the spectral weight, so how many electrons are per this part of a band, is present there in the band. And okay, that's the statement, that's the meaning of this color, but nothing is explained here, so let's just go further. So here, these are the sentences that introduce the model, and they use some adjectives. They use adjective mean field theory, and also independent electron approximation, harmonic and adiabatic approximation. So these are just adjectives which one cannot understand to understand this article. It's not important to understand these adjectives, and also they are not explained here what is really meant there. One of the questions that's here is that why is it a really mean field theory? Because here, when you look at the main formula, you don't see any mean field. And yeah, I can, how to say, speculate about the intuition behind this formula to guess where this mean field, somewhere here in this coupling, for example. But that's the waste of time. The idea is that we will just work with this model because that's a version of well-known Fröhlich model. The only thing is that here we have a more complicated sum. It's sum over all q's. I was like, sometimes that's just sum over just one value, for example, sum over k. But here we have a coupling of many different modes, and A is the operator that corresponds to electrons, B is the operator that corresponds to phonons. That's why we have like omega, h bar omega, because we can have different frequencies of phonons, and epsilon k is the thing that I right now forgot. What is it? Seems that that's just a fully energy of the electrons. So it's not energy from the Fermi-surface. Yeah, okay. Let's just try this question. Okay, that's clearly an energy of a mode, but is it from Fermi-surface or from zero? That's the thing that's not written here. So I'm not sure. And here we have also a n and square root of n, but it's still not clear why do we have such a number here. Okay, but we at least understand what's written here about this number. So that's number of lattice per unit length. And it seems that we just divide this picture into some unit lengths. So I don't know, unfortunately, what can be n equal to. But I have written this question in my list of questions. Yeah, let's check. Yeah. And so there is this integer which is not commented, but one who knows very well basic electron-phonon interaction theory, then if one knows, then one will answer this question. Maybe I will answer myself in a month. it's not in the top priority to really understand right now the fundamentals of electron-phonon interactions. But that's the Hamiltonian, like electronic part, phonon part, coupling of electrons and phonons, and then the typical feature of the Frolics interaction that we have A dagger A and then B dagger plus B. That's the Hermitian conjugate term. I mean, if you do Hermitian conjugation, you will get the same term as you need to rearrange some. So, except that notation is slightly unusual because of, for example, the square root of n or q dependence of the coupling. And also double summation, except this, that's typical Fröhlich Hamiltonian that is always used for electron-phonon coupling. Then, I mean, even here at this point, some framework is assumed, so let me not even try to remember it, because this model, of course, is driven somehow, and it's driven for this acoustical type of phonons which have this dispersion. So that's the acoustical type of phonons. But if we had like optical phonons, yeah, actually it's a good question. That's a good question. What if we have a different phonons? Then, like, I mean, you can remember this theory about polarons, because I was doing a stream about polarons, and I will do some streams about polarons in the future. So here in that approach, they take other types of phonons. So maybe if we go to this direction, we will get some new physics. But here they don't even ask this question. I mean, Rossnagel, he just writes this formula as the correct correct formula for this approximation. Because it's stated that somehow, to some approximately good extent, this modulation can be explained by this phenomena and by this model. And this model assumes some intuition behind it, which goes beyond this article. And I'm also not assured in this intuition that is there. But let's see what all out of this intuition is written here. So here it's written that actually that displacement that was there is connected, I mean, from the whole discussion of modulation of electrons and phonons. So we don't know what is this UQ, because here UN is introduced and U0, but not UQ. But if we take the Fourier, I guess if we write form 2 in a different way and take the Fourier transform, that's how we can get UQ. And we also assume that electrons interact with some potential of the lattice. That's how electron-phonon interaction, I mean, it's how like energy band and dispersion of electron is created in general. And also if we have like phonons, then also it's because of the potential that lattice has. And that's the connection of the displacement of an atom with the potential that is felt by electron. And both of them manifest themselves in this part of the formula and this part of the formula, since this epsilon, the spectrum, really should understand what is the potential of the lattice where electron sits. And the coupling also is very dependent on like initial potential and the potential that was obtained after we have oscillations of electrons of the lattice. Also, it's interesting to note that here we deal with modulation and we link modulation to some static nature, but all this theory of phonons is the theory for like oscillations. So if we have zero temperature, then we should have zero oscillatory modes like created. But this theory works actually even at zero temperature. So there is some real understanding of this model that, okay, let me just write this question for myself. Yeah, it's not clear if are we dealing with real or virtual phonons. Maybe we're dealing with general model that can have some like particular cases of virtual phonons where nothing real is oscillating. And also maybe we can derive this superconductivity, like I mean, to create the question about standing waves. I mean, the real answer is that of course it's applicable, because of course there are phonons, and we just can use the theory of phonons, but I'm posting the question about deeper understanding that, like, we can have just static modulation, and why can we apply a dynamical theory of phonons? Also, we can set the temperature to 0, and at 0 temperature there are no phonons. So why we need to speak? Why can we speak at all about this theory as 0 temperature? And 0 temperature is below the transition temperature, so so why this theory is applicable for chain density wave? That's the main question, but that's a deeper question, and the goal of this paper is to give a review, so I will need to read some cited paper to understand this answer, and that's all. Okay, but that's what happens here, that with that model assumed some displacement of atomic lattice, and there are a lot of modes in this displacement. These modes are omega q. We have some constants like mass of the atom. Okay, actually, let me write here. Yeah, so maybe don't. So my version is that this m is the mass of the total molecule, which, for example, if you have 1010 disulfide, it will be sum of 3 masses. And I don't know why this formula is so. The main thing here is this connection between both things that are assumed in the Hamiltonian that is written. And here is also a formula that I don't understand, because if we have a lot of harmonics, then maybe we should calculate the total deformation using them, and only then plug them to the formula of the lattice. But some idea here is present and it's not written. That's why we have like just one Q, and maybe that's just the wrong formula here, because like which Q should we take to plug here? Maybe we should sum over them, but if we sum, why not to sum like somewhere inside? And because I mean that's the well-known formula for oscillator, but if we have different frequencies, then maybe we need to find the mean, like I mean the real one frequency and the real average displacement, and plug it here, and not just work by the harmonics each after each. So even inserting some here over Q, I think that would be a very bad idea. And okay, here that's the thing that's related to the lattice. here we are coming again. Okay, that's how this explanation is created. So here there is just general statement and the energy of a lattice, then energy of electronic band. There is this negative change of electronic energy, and I don't know how to comment this formula, because I mean, that's the question of derivation of this formula. And on the level of this article, we need to understand that there is this susceptibility. That's the well-known formula. It's also known from Kubo theory of linear response. And right now I don't want to focus on this derivation because maybe it's very easy to find this formula. And I also haven't worked a lot in linear response theory. But the only thing that I know is that okay, this formula is famous. Another thing is that for some reason they write non-interactive electronic susceptibility, because maybe that's the idea that here we deal without this modulation, like with the model without modulation. So without modulation, we have non-interactive electronic susceptibility, meaning that electrons do not interact one with another, they just interact with the periodic lattice. And also, it's not clear for me why this formula is so we take that potential that was obtained and plug it here squared with minus and multiply this thermodynamic quantity. But we should understand this procedure that's the energy of the electrons. And minus is, of course, because of intuitive reason that there is a gap that appears, so electrons are moved lower, and that's why energy decreases. But it's a good idea to have a derivation, to know the derivation of this formula. But for now, I don't know, and it looks not like a typical formula. We multiply potential by susceptibility, squared of potential. So I don't know. But let's go further. Okay, then we need to explain what are the quantities here. So maybe we have sum over all possible modes. Then also f is the Fermi function, as you might guessed already. And epsilon is the introduced spectral of electrons in the Hamiltonian, which I have discussed already. Yeah, and here, yeah, okay, yeah, I will delete this comment about the energy gain because, as I explained, if energy decreases, then we call it energy gain. That's the well-known notation for people who study English. And yeah, if it's increased, then we have a bigger energy gain. And that's maybe approximately a constant, or it should be considered as a constant. So if we change the temperature, for example, I mean, that's the only parameter that we're working with here, the temperature, then susceptibility will change because Fermi function functions no temperature dependence, but the the potential should be like, okay, it also actually changes because UQ should also depend on temperature. So right now we are already coming to the stage of complicated questions, but if we don't ask them, then it's clear that the biggest contribution is from the susceptibility, and that's what's written here in advanced version, direct measure of energy gain, like measure, but we understand the sense of this formula. And okay, the typical criteria, of course, is that the energy change should be less than zero, so it will be more favorable for a system to change its state to charge density wave. Also, maybe we need to assume that we need to select one phonon mode and work with exactly this phonon mode here. and also with exactly mode here, so all modes decompose and don't know one about another. That's how I interpret what's written here. And yes, of course, we need to check if total energy is less than 0 because of this idea of energy gain, which I have discussed already. I didn't check, but maybe it will take less than a minute to check that if we use the previous equations and plug to this obvious formula, we will get the condition. And here, so that's why I was confused throughout this paper, that they start with discussion that they need a strong coupling approach. But that was the important point, that here they jumped to the weak coupling approach. Why? Because that's Rossnagel decided how to speak about it. Sorry. So we are looking at the theory that is not used here, but that will be not used because we need a strong coupling, intermediate coupling theory. But he says that to work with this strong coupling theory, we need to first understand this, the weak coupling theory, and we have this abstract criteria for occurrence of charge density wave. Of course, you can look at, when I look at this formula, I don't understand how to apply it, because we need to get, okay, the coupling is a problem, frequency of phonons is a problem, but, and we need to know which Q to take. But there is also this susceptibility, and I still haven't seen yet ever that it was calculated for some particular material, but maybe one of the future articles will tell me. So that's why I say that that's an abstract criterion, because it's not clear how to use it directly. And the message here is that in these lines is that that theory is not applicable, but we can save this theory, and Chan and Haney have done it for us somehow in this cited paper, and they have given us a generalized version of this criterion. It's not written here. What do we mean? Do we mean a large coupling of electrons and phonons or no? Which we need, we need to believe, and later there will be a discussion of the value of coupling constant, why it should be large. But here we are just told that it should be large, and sorry, I have a message. Yeah, I will reply later. So the main idea which should be here, that this criterion should be generalized for this criterion should be generalized for the strong coupling, but here is generalized for Coulomb and exchange interactions, and that's the condition of the terms here. That's the Coulomb interaction, that's the exchange interaction. So it's not clear if it's really used for the strong coupling or not, because based on what is written, no, it's not used for the strong coupling. We just take into account also some extra interactions that are neglected in the Fröhlich model. And that gives us a motivation for really deriving this model, because it should be like obvious what is taken into account, what is neglected, and suddenly we are dealing with neglection of Coulomb and exchange interactions. So it's just interesting to understand why exactly we're missing these interactions. because I thought that they could be there, right? Yeah, but they're not there, and okay, we have just the link to this work which should explain us what's going on, but we have this strange q-dependent constants which come into our equation, and that's what we are set. Another thing is that there could be a spin density wave which goes beyond this article at all, but generally it could be. So if this criteria is not satisfied, then we can have a spin density wave, but I don't know anything about spin density wave, but I just know based on this sentence what could be if we, and what is the condition of spin density wave, and that's the condition. Of course, I'm not able to derive it. I'm not able to plug this strange Coulomb interaction term, but okay, we have the cited paper to figure out what's going on. And it's also a simplification of these formulas, but that's again just a comment about the theory in this paper. Okay, yeah, here we can basically see what's written here, that when this condition is satisfied, this is satisfied when this term is big, this term is large, and this term is big is when the coupling is big and the exchange traction is big, but the omega, the lattice, yeah, they called omega as lattice strain energy, which is not a good word, I guess, because that's just the frequency. And of course we have formula h bar omega, which will give us energy, but we also have the formula lattice strain energy. And here omega is not that formula, so it's just bad wording. But the idea is clear that this omega should be small and this u should be small. And this susceptibility should be large because it's in denominator. That's clear, of course. But what is not clear is really how to use this equation experiment, and no, I have no idea. But it's written here, but not written explicitly, sufficiently practicable to make contact with experimental data. So some comments will be further, but right now I don't understand this. It looks like an abstract statement and far from experiments. But here it's announced that it can be used in experiment, and maybe that's the only article in the world that uses it. But maybe I'm wrong. Of course, I didn't read the cited papers, but sounds like. I mean, maybe not so many people use this criterion, but I need to read more papers to be assured in this. Here it's written that it's used for experimental data. I just see that it's very hard to understand what are these quantities for some particular material. That's why I don't think that it's easy and practicable to use it for experimental data. Yeah, here they say that Chernetsky wave occurs in strong electron-phonon interaction systems. But I don't know how do we know that there is a strong electron-phonon interaction system unless we have some phenomena. So that's a deep question which goes beyond this article. Can we even say that Chernetsky wave originates from electron-phonon interaction? I mean, occurs in systems with strong electron-phonon interactions, because what are the effects of strong electron-phonon interactions. If it's a charge density wave, then we can say the charge density wave occurs in systems with charge density wave, which makes no sense. But maybe there are some other electron-phonon interactions, effects of electron-phonon interactions of a strong type, and also we can set this correspondence of 1-to-1. If there is a strong interaction, then we will have charge density wave. But it's a big work to check it, to look at experimental articles. Here is just some statement. And here this thing is announced that both phonon frequency and the electronic frequency is changed. Yeah, if we have this charge density wave. And here it's written that that model, which is one-dimensional, but also with these exchanges, will be used for a typical, I mean, it will be more developed. I'm just not sure about these exchanges, that like these energies, coulombs and exchange interaction would be used here. No, it will be not used. They will neglect these effects. And maybe some authors use this extended criterion. It will be also discussed in the later part of the article, but right now this is just comments about general theory. So here they just continue, Rossnagel continues developing the typical theory, and the first step is to insert some tight binding energy bands, and that's already the question. This one. So that's the answer to my previous question. What is this epsilon? Is it from Fermi-surface or from zero? No, it's from zero. And that's this typical minus cosine dispersion of tight binding model. So that's the typical formula for tight binding model, which is in scope of basic theory of condensed matter. So it's better not to speak much about it and pretend that it's very obvious. However, of course, a derivation is needed, but that's a standard derivation, and maybe we'll revise it later when I will be doing stream about electronic properties in matter. But we just use this standard formula, which has just argument here, and Fermi energy and the lattice constant is just a constant. And we're stated that if we use that formula, which I should have written in my collection of main formulas, but I didn't do it yet. So that's the formula that we should use. Somehow, if we plug this cosines and then get rid of a sum, maybe by going to integral, then we can simplify that formula for this quantity and get this formula, which, how long is it? It's have more than 2 pages of the text. Okay, let's finish this page and then we'll have a little break. So that's the formula that appears. We have now density and Fermi energy, which, as far as I understand, should originate from the sum. So we change sum to integral and then approximate this integral. That's how we can get this density of states. And other things like temperature, Fermi energy. Temperature should come from the, of course, Fermi distribution. Fermi energy comes from the energy. And I didn't do this derivation. The main statement is clear that that formula for tight binding model gives us this result. I mean, it's expressed in this form. Okay, so it's not clear here how the second statement is linked to the first statement, the statement about formula 12. So here we see the divergence. So if we set temperature to 0, then we have infinite susceptibility. Somehow, and let's not even touch this question, how this leads us to the new dispersion of the phonons. And we can see this dispersion here. Of course, this link is missing, but that's a big theoretical discussion, which will go beyond this article, and I will do it later. But from the susceptibility, using, I don't even know which formula, and how we can get this generalization of the frequency. Maybe we don't need to use this formula, maybe we need to, and of course, okay, let me comment it like this. There is a Green's function formalism that is always assumed here, and we need to calculate the polarization operator and plug polarization operator, insert polarization operator into the full Green's function of phonons. So this framework is assumed here, and we are presented with the result that that's the frequency of phonons because of the interaction with electrons. And it's a good thing to derive, but right now we don't talk about derivation. We talk about this effect that comes from just basically that coupling, but for one-dimensional system. Yeah. And the conclusion is that at finite temperature will not have a divergence, but if we insert final temperature to this formula, then we can give a 0 for the phonons dispersion. And again, we keep in mind this image, that this should be there. Yeah, and that's also here written. This is the image. And it's not clear very much for me why this softening or going to 0 of phonon mode is linked to the creation of a new phase, but these are the typical words that are pronounced that what's written here? Okay, signals a phase transition to a state with a frozen deformation. So I don't see this real link with the omega frequency goes to 0 and a new state, but I'm not expert in this formalism. That's the famous statement. So anyway, all understanding of the formalism boils down to understanding, oh, if we have a 0 at the frequency, then it means that there is a modulated new state. Maybe if I revise condensed matter, it will be obvious for me. Right now it's not very obvious, but that's the statement. And we see a generalization of the previous formula. There was the formula 1, where there was the wavelength of the electronic dispersion, and right now it's also equal to this P divided by K Fermi. It's also not driven here, but maybe okay, we're just referenced to the typical theory of chernivtsi wave. No, we need just to believe it. Right now it's not very obvious for me why this thing holds, why K Fermi is here. It's like expected, but because also say that the divergence happens at 2K Fermi. So if we insert 2K Fermi, then this 2 cancels and we'll have just a K Fermi. But the derivation should be here to understand it. and right now I understand it on the level of statement. Okay, and we will continue the first part after a little break. So what we have done half of a page, 1 page, 2 pages, 3 pages, 4 pages, 4.5 pages. That's what happened. Not a big movement, but not little one. So see you in a minute. Okay, let's continue it, and we have really a lot of pages, so we need to go further and think more about it, and finally finish today this second and third part of the 5. So the statement here is clear. Yeah, here it's written that okay, the relatively important comment about this formula, that K is because of electronic properties, and electronic properties are based on number of electrons, for example, and energy bands, and it's not clear what exactly can influence the Fermi energy and Fermi wave vector. But in general, this lambda can be different and it cannot coincide with the atomic lattice dispersion. So that's what's written here, that in general is incommensurable, which means that out of proportion does not have like periodic modulation, like we have a modulation of atomic lattice. And I was actually told that there is a theory of, I was reading the theory of electron of charge density wave, and I was given a derivation where they always commeasured, both always commeasured. But here there's indeed a good argument that they shouldn't be commeasured by default. Here, that's the criteria for charge density wave to occur for g squared h omega. And here we also see this thing in the frequency of omega. So that can be considered as the origin of this criterion. So omega squared should be 0 or lower. That's how we can understand that something is wrong in the system. But again, I don't really understand this connection. Okay, let's just write here. Yeah, so this link is missing, but it's not written here and in the previous textbook which I was reading. But like if the very well-known statement is that if there is some strange frequency or zero frequency, then there is a new state, and this frequency can be when this thing is less than zero. That's why we have that criterion. And that's the same question which I wrote, basically, like, what do we mean by that? When we get ultra-normalized frequency turned to zero. So some intuition is assumed here, which is not written explicitly. Also, some theory is used, and it's not written here, but this theory gives us the transition temperature. And we are presented with the formula of the transition temperature. And there is also an introduction of electron-phonon coupling constant. So as we can see, there are two, in scope of only this theory, there are two coupling constants. One is the J, which is in the Hamiltonian. Another thing is lambda, which is another notation for the coupling constant. But lambda is also known like a wavelength, so don't confuse it with the wavelength. Right now, I can't comment much about it because there are other models, other notations where there is also an electron-phonon coupling constant, but I'm not sure that that constant means exactly what is meant here. And anyway, that's just a reference to some book where this formula is deriving. But some standard theoretical approach for this model gives us this result, that this is the transition temperature with this introduced constant. And this omega and j, they are fixed, and a certain wave vector where we have a divergence, so that's q0 that we have introduced in the Formula 1 in the whole beginning of this discussion. Okay. Another strange statement is here that Brillouin zone edges coincide with Fermi points, and that's not what I really understand. Maybe it means that, hey, like here we also have this dispersion, and these are the top points of the band, so no, like I would better not comment this statement that requires really good preparation to the field, and that's not what I have right now. So this statement connects Brillouin zone edges, which are these points somewhere, maybe this point, and this point. They coincide with Fermi-surface. I don't understand this. Okay, I wrote myself this question, and let's go further. I don't understand what is meant really by this sentence. I need to revise basic theory of Brillouin zone and Fermi-surface. It's not obvious when we start speak about some not so template materials. So one of the future streams will be about the electronic properties of solids, definitely. And here, I guess it's written that these are two subbands. That's one band, that's another band. It's not really clear if it's a correct statement or not, because from this formula I don't see that we have exactly this thing. Like some of them should be okay. Here we see that some of them, that for minus it's always below zero, because this term is always, no, it's not always bigger than this one. We have here plus, here we have plus minus. here we have minus, so no, I don't really understand how this formula 17 is consistent with the plot B. And also that's very strange that we always say that gap appears in Fermi-surface, and here it's written that 2 delta, not delta appears. So I don't know how to interpret this formula with this plot, but the statement is that there was one dispersion, one energy dispersion energy as a frequency of k, one band, and we have now 2 bands. Why? Nothing is explained here. I mean, like, Brilliant zone edges entail energy discontinuities. Maybe the Brilliant zone was shrinked, and right now that's the end of the Brilliant zone. But the link is missing, the explanation is missing, so I can only guess what is the reason for this formula. But also I need to derive this formula, and then I will claim that I understand it. Okay. Yeah, and of course, electrons will just go to the lower branch if it's possible. If it's not possible, only then they will go to the upper branch, which is higher in energy compared to the lower branch. And here we see the statement about divergence of density of states. It's also not clear why, and maybe later we'll derive it, but that's the statement here, that also we can calculate density of states and find out that it is divergent. And also call this gap over complete, not sorry, just complete. What is complete? That's not also explained. Okay, here we are given the next formula in scope of this theory that is considered as a basic theory. So we have a gap to delta, we have some input parameters of this theory, and we are given this formula for the energy gap. I mean, for half of this energy gap between conducting band and the valence band. Also, it's not clear, and sorry, and that's the question that is already written, that that why do we deal with a normalized frequency if we actually have a normalization of a frequency? Maybe we need to use the real normalized or normalized frequency, but nothing is commented about it, so it's just a question. Okay, let me write this to the list of my questions. There should be definitely generalization of this theory to renormalized phonon frequency, but nothing is explained here, and I haven't heard about this explanation yet. Let's look what's written next. Then there will be here it's written, and further there will be a lot of comments that there are some chi dependence of something. So if we have, like, basically maybe it's written here that bands can be occupied by different numbers of electrons, which means maybe there are several bands of the same energy. That's how we can explain it, because Pauli principle doesn't allow us to have two electrons, more than two electrons on one state. But there are some generalizations. One of the generalization is to have some momentum dependent of spectral weight. So that's not what I understand. Maybe they mean that there are different number of bands and some states can be here, but some formula is assumed by the statement, and I don't know this formula. So there is a K dependence, yeah. I mean, there could be in some models, so I need to read cited papers to understand these models. Okay, now we have link with the measurements, and let's look at them in my collection of main plots. Here, let's put this thing for a long time. Maybe it will be more useful for us than the schematic charge density wave. So we also work a lot with the spectral function, and it's not explained here what is it. Maybe it means how many states are per energy, but let me not explain much because it's not explained here also, and it wasn't revising exactly basics of spectral function. But the idea is that if we work with any like Green's function formalism or with any other formalism in condensed matter, then there is this typical thing as a spectral function, which we can try to derive. And why is it useful? Because there are some ARPES experiments, and I was maybe mentioning them already in the previous stream. So we know that they are there. They give us Fermi-surface or electron bands in different directions. And the spectral function plays a lot of an important role for this explanation, but which exactly is not the thing that I know. But we're given the formula for the spectral function for this model, and here in the 1b, here we are given this maybe formula that E minus E1, E minus E2. So maybe E1 and E2 are this and this energies. So we have these divergences. Another option what can be is that, to put it upper, that this and these are the points where there are divergences. Okay, here there is a comment about this bold line, which I don't really connect well with this formula, but everything is about the same topic. So here they say that this bold red line is only at the place where there was initial dispersion, but also here in these points Fermi, there is more spectral weight in this second band that also appears, and I guess that's what happens. That I mean, that's also what is shown here, that before we had just one band, now we had two bands, so a drastic change happened in the spectrum of the system. And maybe this A formula is describing us this big, I mean, let's say bold red lines. and they're related to some back bending effects. I don't know what is a back bending. Yeah, so some effects observable. And they also say that some novel periodicity is not there, but what is this novel periodicity of the function A? It's not the thing that is explained. Okay, I killed the mosquito. Let's continue. That's important for my good health. So we have another statement which I tried to understand and explain, at least somehow. So we had this formula for the change of band energy. That's the formula, so maybe we need to also sum over all the frequencies. And here we say that we go from that formula to the occupied electron states and simplify that formula for this case to this formula. That's my interpretation of what's going on. And that's how we can get, after some minimization of two formulas, and let's see the first formula. Yeah, that's maybe the first formula, which maybe I should also have a sum, but nothing is written and explained here. So we are given several formulas, and if we minimize total energy, then we can get the energy gap. That's how we are proposed to calculate it. And reminder that before we were stated a similar expression with the exponent for the transition temperature. And so maybe it follows from this. Yeah, I should actually, I understood this formula better. So how do we get this formula? Oh, actually, we know that this thing should be 0, so this thing should be 1 in order to have a transition, and we just plug the known formula for the susceptibility, and this formula should come out of this thing because even 2.28 is there. And that's the origin of the first formula, which is about transition temperature. And after discussion of bands, of the gap and the spectrum, it's not really clear how this formula is consistent with this formula, but we're given the second formula of the gap. So maybe if we take the zero temperature of this formula, we should get this formula. It would be strange if they would not coincide, but that's my explanation of what happens. And right now we notice that these formulas are relatively similar for transition temperature and for the gap, and that's how we can write them together, the gap and the transition temperature. And it's called BCS relation. So all of it can be seen as a special framework for superconductivity, because BCS theory is exactly about the superconductivity, but here it's for one-dimensional solid and interaction of electrons and phonons in one dimensions. So that's a new approach for me. I wasn't studying this approach, but we got a lot of well-known things here: the normalization of spectra, the change of the energy, the modulation and change of energy is characterized by the gap. And I don't know. Wait a second. Okay. Okay, I have another message. Yeah, when you do business, I have many messages, but it doesn't mean that it will move somewhere. So we also have actually this important part of the theory that tells us that actually this lambda should be less than 1, which is maybe, I mean, that's of course common sense tells us that that it's about weak coupling, but the problem is that we were thinking about weak coupling in terms of little g, and we said that this little g should be less than 1, or at least that's what I imagined. And here we are already working with lambda, and there were no comments about lambda except the definition, but I know some statements about lambda which are better not to say because they are related to polarons, and all this theory of Chernysty wave and polarons, they stem from one theory about the electron-phonon interaction. So that's the topic for the future streams, the real theory of Chernysty wave and of electron-phonon interactions, because that will answer us this question, like, what do we really mean, this lambda or little j should, and what should g, maybe not j, g equal to if we speak about weak coupling limit. Okay, let's read the comments which they give later. Okay, here it's written that this picture may have weakness, but as it's written here, we have just collection of statements from different cited papers, so I doubt that we can call it a one picture, because I'm not sure that we can drive everything here from just one starting point. I need to double check that these formulas stem just from one model. That's like a good piece of information, a piece of science where we have like results of this model, but I suspect that it could be a collection of different approaches. Here there is, remember this sentence that's I consider as a useless sentence, because like that's well-known part of quasi-one-dimensional models, that actually should be somehow generalized for three-dimensional models, and only then we can discuss physical sense of them, because by default there could be some divergences because of fluctuations. This is a well-known statement. Currently I haven't reached the point of understanding that how to derive these fluctuation effects, and how to prove that actually they do not destroy the system, because like embedding two-dimensional, three-dimensional space is enough to fix it. But okay. That's just abstract comment which you can read more about in this cited paper, but that's basically not gives us no really useful information. You can make this comment for all the quasi-one-dimensional systems, and still people work with them, because I guess there is a good answer, good reply on this comment, but I wasn't reading this part of this theory. Okay, so I was reading this sentence 3 times right now, and I have no idea what is meant here in this sentence, even though I was reading it before. That's just useless sentence which has no sense. It tells us that also electron interactions are included, which we already know because we know this criterion for the instability, which takes into account also electron interactions. And that's the only useful thing in this sentence. I should mark the sentence as useless because like some strange comment about stability. Yes, like maybe it's meant that we need to take electron interactions into account. Ah, okay, I understand this sentence, that it's meant here that by stability that we mean no parallel instability. So if we take into account electron interactions, then we will not have the parallel instability, but we measure parallel instability, so it means that it's not clear how to deal with electron interactions, and anyway we need to use both of them for this model. Okay, that's a meaningful statement, and just links us to the electron interaction theory from this cited paper. Okay, basically that's it. That's this model. I showed you main plots and main statements which are taken from the articles. Of course, it's not explained enough here what is really meant by this and why such formulas are here, but at least the connection between them is already clear, that that's the model, that's the assumption for the model, that's the energy which can be obtained from this model by some well thought transformation, and that's the criteria for the transition. And if we have a transition, that what does it mean? That susceptibility diverges and frequency diverges. But actually maybe that's not true. The truth that, because susceptibility here diverges at 0 temperature, so at finite temperature it will not diverge, but if it diverges at 0, then that's the sign of instability which we follow and get the formula for normalized frequency, and later for the change in bands, and also for the change, basically change of electronic spectrum, which consists of creation of 2 bands and the gap, and also transition temperature, and also spectral weight on the gaps. Basically all of this is just electronic properties because of this interaction. So that's the standard theory with some advanced comments, and now we will discuss 2 things. It's like about what if we have a different coupling, and what if we have a different dimensions. And I feel that today we are not going to go to the 4th part of the lecture, for the 3rd part of the stream, because it's a hard article actually and requires me to think really a lot. Let's just check how much do we need. 1 page, 2 pages, 3 pages, 5 pages, 6 pages, 7 pages, 8 pages, 9 pages, more than 9 pages. So definitely we will not go to the 3rd chapter, and I will be just streaming, and that's how it's only possible to go through this article. I underestimated my skills, and this article is a too big article. I need to adjust my approach actually for such big articles. But okay, we know the model. Let's just discuss the question about weak to strong coupling. And the well-known answer is that it's not clear about what will be, and a lot of effects will appear if we include the strong coupling. But let's read. Okay, that's what's written here, that most formulas suddenly cannot be applied. Why? Maybe it will be explained below. I don't know why. Because below, above, nothing was written about the limit of applicability in terms of coupling. So I can't tell you why. Okay, here there is just a statement like, what if we increase, then there will be bigger lattice distortion, bigger energy gap, and smaller coherence length, but we're not there's no explanation what is this coherence length that is connected to this change of frequency. So a new parameter suddenly appears, and also it's not clear as it's written here in my question that distortion amplitude yes, so maybe it means that we have, I mean, I don't know like how to understand it, because P Fermi is related to the properties of electrons. So if we increase the coupling of electrons and phonons, then properties of default electrons should be the same. So we don't understand why do we need the larger distortion. Why larger distortion will be if we increase the coupling. For me, it looks strange. And also, what is the coherence length and of what? It's also not explained here. But okay, we'll end this question later. Okay, maybe that's an important statement. It's also not clear what do we mean by weak or strong coupling. Do we mean lambda? What do we mean J? I mean, we mean both, but what can we say about J? G? Yeah, I don't know what can we say about G. But also there is this at least somehow clarifying statement that that's the border that we need to figure out what is delta and divide by device frequency, which is the highest frequency. But also, like I forgot, so okay, definitely one of the next streams will be about electronic properties of solids, because I forgot in the bias model we do the cutoff on the frequency of the bias frequency, and here we don't have such a cutoff, or the bias frequency is the same the bias wave vector. Yeah, maybe that's the bias frequency, the highest frequency that's possible. Um, okay, so that's just lack of my preparation, and suddenly device frequency appear, which I can only guess why is it so. Maybe that's just the highest frequency, but also I don't understand this statement of the delta divided by h omega dBi, and also maybe mean delta zero temperature here. That's what's written here. The origin of energy gain is electronic. That's a useless statement because, yeah, because it doesn't tell us anything. Of course, there are electrons, so of course they're involved. that's obvious. Okay, so I understood that today we will cover only the topic of what if we increase the coupling, and later part will be for the next stream because I'm rather tired, and I also forgot what I was reading about here. I went to the 3rd out of 5 chapter, and that's the 2nd out of 5 chapter in section. So I need to rest a little bit longer, then continue. I'm just trying to understand that what is meant here. So it's like energy gain near Fermi, near this, or this, maybe this still point. Okay, so we are given a statement which is not explained, but the meaning is that we have two cases, like small gap and large gap. In one case, the energy gain is around these points. But now if we have a large gap, then energy gain is proportional to delta and spread over the whole brilliant zone. So here we don't see this plot, but the idea is that if we had a large gap, then this plot will be way, way more different. It will change in a very strange way, such that all this energy will maybe change such that energy gain is spread over the entire brilliant zone. So we need to read this cited paper. Only this is the way how I can understand, how one can understand what's meant here. I guess that it's meant that this dispersion will change drastically, and we will not see this, but we will see also a shift somewhere maybe below of the gap. But maybe it's also about that's about energy gain, so we need to calculate somehow this energy gain, and I don't know how this is calculated. We are given this formula from nothing, maybe, or from the previous formula where we need to plug something in. But okay, the main message is that that formula gives us very different quantity if we use a different strength of coupling. Maybe it means also that spectrum will be changed also in a different way. Not only the gap will appear, but also the bands will move, shift somehow. And that's also maybe related to this statement that importance of Fermi-surface is reduced. Again, in this case, which we discussed, when there is a big coupling, if the coupling is increased. what is the role of Fermi-surface in all what we have discussed? It's very unclear, and this statement is also very unclear because everything was like so simple, and here basically it says that there is a different theory that works differently. That's how I can interpret it. Because like Fermi, what is the importance of Fermi-surface for the low coupling? I don't know. We just have a theory with some formulas in the middle of derivation at the end of the derivation. But what is the importance? No, I don't really know. So the conclusion is that just there is a different theory for a strong coupling, and we have a citation for this model. Okay, now also told that there will be different thermodynamics. Currently we have studied nothing about thermodynamics, but it will be still different. So maybe that's the place where we should again use our general knowledge about condensed matter, that at low temperatures exactly electronic entropy plays the key role, not the lattice entropy. Yes, and that the gap vanishes completely. That's obvious from the definition of T0. And that's already a statement that I'm not familiar with, that now we have a different case and we have an entropy of a lattice. And I can't explain it really. And I mean, if we spoke about heat capacity, then I could remember that, yeah, there was a contribution from lattice and from electrons or thermal conductivity. They're related to entropy. But here it's written about thermal disordering. And what is thermal disordering? It's really already not clear. But here we're also told that the transition itself is driven by the entropy of a lattice. So that's a collection of very unclear statements. Like the transition is driven because of coupling of electrons and phonons. That's what we were told. But how the transition can be driven by the entropy and why is it exactly entropy of a lattice, that's not what I can't comment anyhow, but there should be somewhere a link. Yeah, these two papers. So these two papers should help understand what at all is meant here. And what is the long-range coherence? It's still not clear. We, of course, remember this origin of this not clear. So coherence length is somehow related to Kohn anomaly, but it's not explained there and here what is really meant by this coherence length. So let's again just forget this statement unless we go to the cited paper 39 and look what's there. But yeah, it seems that the conclusion is that if we speak about the phonons and lattice, then there is a coherence length, which is assumed as the parameter that describes the lattice. And of course, I can try to guess based on the name of this parameter, but I want some formulas. And okay, I have some formulas in my head, but they are rather not the ones that I'm assured in. So okay. And of course, above T0, there is undistorted state. And right now I'm a little bit confused because somewhere I was reading that, I mean, somewhere in this paper I was reading that we have like also above transition temperature some distortion, and all the way above the transition temperature we will have the undistorted state. And here it's written like it will be restored. So let's remember this statement, and I will return to another statement when I will find it. Okay, but that's what I expected, that above T0 we have initial undistorted state. I will just come to this statement again when I will below match, like see some statement that contradicts to this statement. Okay, we have three basically paragraphs because, I mean, yeah, paragraphs in the sense of a text before the end of the stream. Okay, now we are told that there is another model which is not explained here, but it's called Macmillan's model of this charge density wave, and there is a formula for the transition temperature, which we of course will never be able to use because we need to know some distortion amplitude, which is, I have no idea how to obtain, and some measure of electron electron lattice coupling, which is now already C, so that's the third measure out of, and before there were lambda and G, and here we have the C. Okay, so we have no idea how to use this formula, but we're told that there is another theory where there is another formula of transition temperature. And nothing is written here to understand better what happens within this theory, but it's written that there will be significant deviations because that was the previous formula. This is the new formula for the strong coupling case. They are absolutely different. We have no idea why they are, like from where they originate and how to use these formulas. Rossnagel just concludes that this BCS relation will not work and gap will be bigger than T0. In the previous case, we had inequality here. Why is it bigger? Like if we have bigger electron-phonon coupling, then there will be bigger gap. So here we have some statements from another theory, which is not explained here, which is maybe useless, but who knows? Just the point is that later, as far as I remember, there will be no mention of this theory. So it looks like a paragraph of useless comments. But if you asked what to do if we have a strong coupling, so maybe the answer is that just use this strange Macmillan's theory. And we have two more paragraphs before the end. Okay, so here we're written that if we go even further for the stronger coupling, then the picture will be even more different. What do we mean by pictures? We mean maybe the formulas that are written and the properties that are here done, but it also boils down to experiments, so we need to really look at the experimental plots and check what are the distortions of the electronic bands, and then try to connect it to a theory and get some collections for different materials, and then try to find out what is the value of the expected coupling between electrons and phonons, and that's how try to understand what is known about it from experimental side. Okay, it's also related, this coupling is also related to coherence length. It can be or low coherence length or high coherence length. And maybe that's one-to-one correspondence. So parallel instability works for, of course, we are speaking only about one-dimensional systems or quasi-one-dimensional systems, which can be described by one-dimensional systems. And here, parallel instability, all this previous theory can be applicable because, as was said before, it was written for the little coupling, little value of coupling. And unfortunately, I forgot to comment these sentences, so maybe I was even not reading them before. Let's read them right now. Okay, so we are referenced to the previous theory. And okay, in that theory, long range order wasn't explained in this review paper, but it's written that in some cited papers it's explained. What do we need to explain? It's also not the thing that I know, but some long range order. And incommensurability is explained by this not matching of Fermi and like wave vector of distorted lattice, which is somehow defined by Q0 as far as I remember. Okay, I actually forgot, but let's just look at it. I can open it right here. Yeah, it's lambda 0. Yeah. So in the case of commensurability, they coincide. Okay, but we need to double check this statement from somewhere. You remember there was the point where I was speaking about this Q0 and Fermi, and they understood it. But okay, in the case of commensurability, non-commensurability, then that they should not. I mean, it should not coincide with the lattice deformation. And that's why maybe we have these two different formulas here in the whole beginning, and I was thinking like why they are not so, why they're not the same, because we don't have in general commensurability. But still it doesn't answer the question about this ansatz, why this ansatz is used at all. No, but okay. We just have referenced that they are explained. If you anyway need to know how they are explained, and cited papers maybe can help. So here we are referenced to the local chemical bonding picture, and seems that that's a famous picture because I was hearing about this picture even last week when I was discussing some of these articles with some clever people in my institute. And this local chemical bonding is when we maybe introduce the chemical potential and vary it locally. That's just another idea about strong coupling theory. And we also said that if we have bigger displacements, then other terms should be introduced in the Hamiltonian, which is of course the thing that is expected, but it's very unclear how exactly one can do it. I also don't know, it requires a good preparation in electron-phonon interactions. Uh, so what is meant by pairs, like atoms attending that atoms tend to form pairs? Maybe it's meant exactly like this, that they are paired, so something similar happens. And it's written that maybe this chirality wave becomes very often commensurate. So what's written here, locked into underlying crystal structure. That's the reference for commensurability. So basically it's written that somehow using that special approaches of local chemical bonding, then we can get this this commensurability because of just this statement. I mean, it's not explained, it just stated that we have this, as it's written here, lock into the underlying crystal structure. So yes, that's just announcement of some results from this theory that is not explained at all, which is a topic for special articles. And also we have a really strange statement that, I mean, that's obvious statement, but it's a statement which is very hard to understand. Why we have, if we have two different pictures, then we can pass continuously from one limit to another. Like intuition tells us this, but if we, I mean, that's really an important thing to understand in scope of this theory. And sounds like very, very hard activity, because usually two different theories and different limits, they look very different. And here it's a surprising for me statement that we can do some continuous transformation of something and get of one model and get another one. Um, okay, here we have a useless sentence where it's written that there is this Young-Taylor effect in molecules. Yes, it's there, but we are not really interested in this. There is an analogy. Yes, you can read about this analogy. There is very little probability that I will open this article and try to find out this analogy. Maybe after, I don't know, 10 years if I be really bored. But okay, I would need to learn what's going on in molecules for it, and it would take at least, 3 days. And there's no motivation to do it. Okay, the final statement at the end of this section is that we don't know what to do in the intermediate regime. However, we were told that we can continuously pass from one theory to another. It looks like a contradictory statement, because intermediate regime, something in between both theories should be. And also we know that there are some polaronic transformations which use absolutely different adjectives when they do their transformations. But yeah, maybe we can think about some bipolar ones, but that's already an advanced field where nothing is known in my head. And maybe one can speculate that bipolar ones are exactly these deformations. Sounds like a great way how to connect both theories, but that's not what I know how to do, because I don't know any either of these theories. What's written here? Okay, it's written just that maybe you can look at electronic structure and some local chemical bonding. So it's not written how to look, to what exactly to look, but maybe you can find something for intermediate regime. However, in Polaronics theory, there is one transformation which works in part of the intermediate coupling regime. And that's what's written here. And let's look at the table. Okay, so let's just consider this table as the summary of what's written here for the weak and strong coupling. Of course, it's not explained what is meant by these parameters. And I have already answered this question, how they tend to be commensurate. I mean, it's not how is it, it's like when we have a, how to say, matching of the modulation of electronic lattice and the atomic lattice distortion. I mean, periodicity of both lattices. And here it's written like local chemical bonding, which is a good theory to read. So let's summarize this paragraph. And here, like, really, it's hard to extract something useful. These are citations and comments. There is Macmillan's theory. Like, really, I was reading it 2 times before I was doing the stream. Right now I have discussed all what happens in this paragraph, and it's still hard for me to do some good summary of what is the real value. Basically, I shouldn't remember it, but the real value is absent here. It's just introduction to the different approaches for strong coupling. However, the model for strong coupling is not discussed, so we are presented with some statements. What's written here? Yeah, okay, we will have a different thermodynamics in 1 second. So we have some statements about thermodynamics. We have some statements about the energy gain. We have a limit, a boundary between weak coupling and strong coupling. We have some comments about Macmillan theory, which may be a great theory, but it's not written here that it doesn't work. And here there are some other ideas about generalizations, which maybe go beyond all the theories that were announced before, and some analogies. And the conclusion is that we don't know. So looks like a very scattered review, which doesn't point out us what is really valuable, what is not valuable, what is working, what is not working. But this is just one paragraph that gives us useful literature to read later. And maybe Rossnagel went deeply through this literature and he understands it. He was just don't motivated enough to write explicitly. And unfortunately, discussion of dimensionality is a complicated discussion. So let's continue at the next stream. So the question is that what if we have two-dimensional systems? And another thing is that what if we have, as far as I understand, several bonds, then we'll have electronic insulation stability, which is a purely different approach, but it gives similar results as it was written here. And yeah, and it's written that it's not really a useful model. It's just an interesting model, which is good idea to learn in order to understand like this case of several bonds, because based on this picture, we have a lot of bonds. So that's was one of the questions that I wrote for the future parts of the article, is that what if like if we have a lot of bands, then we need to take into account these bands, that they interact somehow, but we don't, I mean, I haven't seen any paper that takes into account different bands. And that looks like a big problem, so I need to really learn more about energy bands in order to understand the applicability of models. So during next stream we will finish chapter 2 or section 2, and the third one will be about basically again review what if we have charge density waves and we have these like periodic distortions, and we can write some formula for it. I will discuss this plot that I was already discussing before. Then there are some comparison of the weak coupling, strong coupling, the gap, because the gap tells us the criterion of, is it like weak coupling or strong coupling, or maybe I confuse it, maybe it's about dimensionality, it's like one-dimensional or two-dimensional plots, right? Okay, there are these two factors and I might confuse them. Maybe it's about dimensionality, maybe it's about the coupling, the strength of coupling. And there are a lot of comments, and there is a maybe useful table with experimental data, and that will be the stream after next. So there will be a lot of streams. So, okay, I'm confusing the buttons again. So it was a really nice stream. I learned a lot. I learned that I will not have enough time, and I had to press this thing because right now it's already evening. It's not already the day when I started the stream. So, okay, maybe I should do this. Yeah. So the conclusion is that there is this charge density wave. Let me try to just summarize in a very short way what I have covered today. So there is this model of charge density wave, which has a lot of standard predictions, like the gapping of the material, but it will be later written that it's not applicable. So we have started discussing not only the basic features in scope of this model, which is not an easy model actually, as you saw these formulas. I would struggle with derivation any of these formulas. It's also important thing is that we need to learn like one consistent derivation, not like I did. I was going to the direction of Green's functions, and turns out that I don't know how to work with Green's functions to do further progress in this direction. But okay. There are some cited papers which I will look at, but in general, we understand these features which appear for phonons and for electrons, and we know some general features of the strong coupling limit, case of the same theory. Some statements contradict one another, some statements are not, a lot of statements are not clear, but okay, now we know more about charge density wave and what would be if we consider strong coupling. So thank you for your attention. Next stream will be tomorrow, maybe in the morning. Bye-bye.